Hello everyone and welcome to the last video for chapter 5 dealing with kinetic molecular theory of gases. And so, before some of you start freaking out just by this title, just let me remind you of what this actually means. Kinetic just means motion. It's just a form of energy that is associated with things moving around. Molecular just means we're talking about molecules. And so the kinetic molecular theory just states the fact that things move. And especially because we're talking about chapter 5, we're talking about gaseous molecules. They move around. And so one thing I did try to state at the very beginning of this chapter 5 videos is that gases don't really care about our rules as far as solids and liquids do. We can put some constraints in solids and liquids because they are incompressible. These atoms are already touching one another, therefore they have some rules they already kind of inherently have to follow. Gases, on the other hand, do not have these particular set of rules because they just spend all of eternity bouncing around, everywhere, anywhere you can imagine. And so in order for some of this math to work out, in order for us to kind of define these as ideal gases, we have to put a few restrictions on how we view these gases. And because of this, please, huge side note here, make an asterisk or highlight it in your notes, whatever you have to do. These rules don't really exist. And so they do exist, don't get me wrong there. These postulates do matter, and they are part of the kinetic molecular theory. What I mean by they don't exist is they're not really real. And so what I mean by that hopefully will make a little bit more sense by the end of this chapter, or by the end of this video, but just kind of go along with what I'm trying to say for right now, just nod your head and smile. And so postulate number 1 has to deal with the volume of these atoms. And so if you imagine a container full of gas, and again, you can put a lid on this container if you'd like, but if you have a container that you are saying contains gas, because gases expand indefinitely, you usually state the fact that the volume of the gas is equal to the volume of your container, which again, from our point of view and from our perspective as human beings, that's perfectly acceptable. But you have to remember the fact that all atoms have mass and take up volume. If not, then they couldn't be called matter. We wouldn't be talking about stuff that exists. But if we were to take that into account when we're talking about volume, technically the volume of a gas would be the volume of that container minus the volume of each of those individual gas particles or molecules, which is a whole lot of math that you don't want to get into. Because first you would have to count each individual gas molecule, then you'd have to determine the volume of each of those individual gas molecules and particles, then you'd have to subtract the overall volume of each of the gas atoms from the total volume, which seems like a whole lot of math you don't even want to start getting yourself associated with. And so postulate 1 just states the fact that it is safe for us to assume that the overall the overall volume of the gas is going to be so large compared to the individual gas molecules' volumes themselves that we just assume that these gas molecules have a volume of 0. But please, again, you have to understand this is just a rule that we kind of set up for all of our other calculations to work. Gases do have volume. Gases do have mass. But in order for our brains to comprehend everything about these gases, we assume that the total volume of the individual gas particles is going to be 0. And so that way we can assume that the total volume of our container is equal to the total volume of our gas. Postulate number 2 has to deal with the particle motion. And so again, we assume that gas particles are going to travel in constant random straight line motions, except whenever they bounce off each other or when they bounce off the container wall. And so again, constant straight line motion. This means the fact that even you as a human being, as you're walking through the air, again, just walking through atmosphere, that you're not infecting or impacting any of these gas particles. That even though you're walking through these gases, the gas particle you just smashed into, again, quote unquote, didn't move. And so whenever we assume that they travel in straight line motions, we're kind of ignoring the fact that gravity exists, friction exists. These container walls might not be perfectly smooth, and so therefore you might not have a perfectly straight line motion. But as I stated before, in order for PV equals nRT to make sense in our brain and for it actually to work out on paper, we just have to accept the fact that these particles, not even accept the fact, accept the assumption that these particles are going to be moving in constant straight line motions for all of eternity. And the third postulate is the one that you should probably have a little bit more issues with. And so postulate number 3 talks about how these things are going to collide with one another. And so whenever I say the term elastic, or when I say collisions are elastic, you can kind of think about this as rubber band. And so if you pull a rubber band as far apart as possible and let go of it, it's going to snap back to its normal size. And so whenever I talk about collisions being elastic, I mean that these atoms are going to bounce off the wall with the exact same amount of energy that they hit the wall with. Which, again, as a human being, you should understand you should probably not run smack dab into a wall. Because you running into a wall, that wall is not going to be elastic. That wall is going to take a huge amount of energy when you smash into it. The wall is going to probably still remain standing. You fall down to the ground with a headache. And the reason is because most collisions are not elastic. It takes energy in order to smash into a wall. Don't really think about it too hard. Don't test out my theory. I promise you. And so if you were to run into a wall, you would lose some energy by hitting that wall. But again, particles of gases are going to just kind of keep this whole thing elastic. Same amount of energy before and after you hit a collision or you hit something else. And the last kind of part of this postulate that I feel most uncomfortable even talking about is the fact that particles do not influence each other by attractive or repulsion forces. But again, they do. And so if you have something that is a polar molecule, like HCl, remember the fact that HCl has a partial positive end around that hydrogen and a partial negative end around that chlorine. And so if you have a sample of HCl, you're not going to have any of these two molecules line up perfectly right next to each other because that H plus doesn't want to be next to the other H plus. And again, that partial negative portion of the chlorine doesn't want to be around any of these other partial negatives. And so if you have these things randomly straight lines, if they kind of come even close to one another, it's going to start deviating. But in order for all of our lives to make a whole lot of sense and be a whole lot easier, we have to accept postulate 1, postulate 2, and postulate 3 as correct and, again, huge assumptions, but it just works out to our advantage that the ideal gas laws helpfully, or luckily, kind of account for all of these instances as well. If you want more explanations about what I mean by, they explain this stuff, please check out my slides and please look at the book. In my slides, I have a couple examples that actually show you how, postulate number 2 and postulate number 3 explain how pressure works or why pressure works. But please, take a look at the ones that I have on Blackboard. And definitely, you should be reading your book, but if it goes without saying. But again, read your book in order to make sure that you have a deeper understanding about all these concepts. So, let's get to the kinetic portion of this title here. Kinetic energy, as I mentioned before, just talked about motion. And so one thing I need to make perfectly clear on this slide, and why I have it in big, bold red letters here a couple times, is at a given temperature, all gases have the same average kinetic energy. Please note, at a given temperature, I'm not telling you what the temperature is because, again, it doesn't matter, but at a given temperature, all ideal gases have the same average kinetic energy. And please notice how I say this. Same energy. Please notice I say same energy. I'm not saying the same identity or the same mass or the same speed or the same color or the same density. I'm saying at a given temperature, all gases have the same energy. And so you do not need to be concern yourself with this equation, The main reason why I put this in here is because I just want to show you that the kinetic energy has some type of relationship between mass and speed. And so because I'm saying at a given temperature, all gases have the same energy, the energy again is going to be the same for all gases at a given temperature. But the mass and speed are going to be kind of like variable. They're going to change depending on what gases you're talking about. But this all kind of goes back to heavier things moving slower, lighter things moving faster. And so in order to kind of help illustrate this a little bit further, you have to remember, let's bring back my old tiny mouse and my big elephant. And so if you don't recall this, go back, and I started talking about these two guys whenever I was introducing the concept of units. But if you have a very tiny mouse and a really big elephant, if you give both of them the same amount of Red Bull, and so if you have one of those 24-ounce high-octane Red Bull energy drinks, if you gave, and again, not sponsored by Red Bull, but if you have the Red Bull, and if you give a 24-ounce of Red Bull to a tiny little mouse, that mouse is definitely going to feel the impact of that Red Bull. He's going to be running laps around inside of the house. He's going to, again, probably have a heart attack because of all the caffeine you just gave him. But if you give that same exact 24-ounce Red Bull to an elephant, he's not going to feel that same amount of energy in the same form. He's, again, might feel a little bit of a hiccup, but he's really not going to kind of respond the same way the little tiny mouse did. And so, again, same amount of energy, same exact can of Red Bull. If you give it to a tinier mouse, he's going to be moving like crazy. But if you give, again, a heavier elephant the same amount of energy, he's going to be moving slower. And so at this point, you need to, again, do not write down this equation. Don't kind of try to commit this to memory. But let me go back one more time just to make sure we're on the same page. At a given temperature, all ideal gases have the same kinetic energy. Energy will kind of, again, be the same, but it's dependent on your mass and your speed. Lighter things move faster, heavier things move slower, with the same amount of energy at a given temperature. And the reason why I bring that up is because, again, EK, kinetic energy, also has another equation. In this case, as I mentioned, don't bother writing this down or memorizing it because the equation's not the important part, but the relationship is. And so, for example, this 3/2, it is a number, 3 divided by 2. If you want to get fancy, you can also say 1.5. But it's a number. It is not a variable, it's a constant 3/2. R is given the name ideal gas constant, meaning the fact it's also a constant. This Na is just another notation of talking about Avogadro's number, 6.022 times 10 to the 23, or a constant. And so in this case, that's a constant, that's a constant, that's a constant. And so this equation now really just saying kinetic energy is equal to some constant times temperature. Or again, kinetic energy and temperature have a direct relationship. If you increase the temperature, your energy increases as well. If you decrease the temperature, you decrease the energy. And so all I'm really trying to say here is I do not talk about the identity of your gas. I don't talk about the mass of the gas. I don't talk about the color or the density or the speed of the gas anywhere in this equation because it doesn't matter. At a given temperature, all ideal gases, regardless of their identity, has the same mass. And so here, temperature, energy, no, I didn't say mass, has the same energy. Whoa, that was messed up. Let me try that again. At a given temperature, all ideal gases, regardless of their identity, has the same energy. And so all I'm trying to show you here is that temperature goes up, energy goes up. Temperature goes down, energy goes down, regardless of the type. And so the last two concepts I really need to kind of talk about have to do with how these gases, again, move, or the kinetics of these gases. And so the term effusion is used to describe a gas when it escapes out of a hole. And so if you imagine that you blow up a balloon, you tie off your balloon so no gas enters or escapes, but then you poke a tiny little hole in your balloon. Not enough to, again, like pop the balloon, but just a tiny little hole in which you can kind of hear some of this gas start to escape. And so if you have a helium-filled balloon, in which case you have nothing inside of that balloon except for helium, that helium is going to have a rate of effusion. And so the rate of effusion is going to be inversely proportional to the square root of its molar mass, which kind of goes back to what I just mentioned earlier. Heavier things move slower, lighter things move faster. And so this, again, is talking about the rate of effusion, or the rate at which this gas is going to escape out of the balloon, is going to be inversely proportional to the square root of the molar mass. And so a lot of students can get this part. They get the inversely proportional part completely fine, but then they forget the square root. So don't forget your square root, people. But please notice, I'm not talking about the identity of this gas. I'm not talking about anything else. I'm just saying heavier things, again, heavier things, molar mass, are going to move slower, and the lighter things are going to move faster. Inverse relationship between the square root of the molar mass and the rate at which these things escape. Whereas if you're talking about two gases, now we're talking about diffusion. And so diffusion is the movement of one gas through the other, or how one gas flows through another gas. And so if you have a balloon, and instead of filling up with helium, say you fill it up with your breath. And so again, as much as some of us would would love to ignore this fact, you probably breathe out a little bit more than just carbon dioxide. And so whenever you blow up a balloon, you're actually blowing up a bunch of different gases inside that balloon. But using the same concept that we just mentioned in previous slides, heavier things move slower, lighter things move faster. And so if you blow up your balloon using your mouth, you tie up that balloon and you poke a hole in there, now you have a couple different gases that are still trying to escape out of that tiny little hole. But the heavier things are going to be moving slower. So things like CO2, they're going to be moving much, much slower inside that balloon. They're still going to be bouncing off the walls, but they're going to be moving much slower in something like H2. Or again, H2, so CO2, that would be 12, there's about 44 mass. Whenever you talk about H2, that's about 2 grams of mass. And so because your H2, again, at the same temperature, all of these gases inside that balloon have the same amount of energy. But because your H2 is bouncing around a lot faster, it's going to find that hole a lot quicker, and all the H2 is going to be able to escape much, much faster than your CO2, because your CO2, again, is going to be bouncing around a whole lot slower. Same rule still applies. We're still looking at an inverse relationship according to the square root. You just need to pay special attention to the inverse of these relationships. By that I mean rate of A, and again, A and B, these are just arbitrary assignments. I don't care what gas A is and what B is, it more or less kind of depends on what ratio you're looking at. And so in this case, rate A is on top, rate B is on the bottom. And so whenever you start talking about how these things are going to diffuse between one another, same idea. Inverse of the square root of the molar mass. B is going to be inverse of the square root of the molar mass. So that's why A is on top here, rate of B is on top there, but whenever you start talking about the square roots of the molar mass, A goes on the bottom, B goes on top. In this last step, I'm just combining both of these square roots, but the same idea still applies. A started off on top, B on bottom, so A needs to be on bottom and molar mass to be on top. For example, if we have a mixture of helium and methane and we place it in an infusion apparatus, I want you to calculate the helium to methane ratio of the effusion rates. And so because this particular problem gives you a very specific ratio, I'm telling you calculate the helium to methane ratio. Then for this one, I would write it out as helium is going to be my gas A and methane is going to be the gas B. If they swapped it around, then you would have said your methane would be B or A and helium would be B. Sorry, backwards. But the way that I have it written out here, I'm asking for helium to be on top, methane to be on bottom. And so the next thing you need to remember is effusion is always going to have to deal with the square root of the molar mass, not just the molar mass. but not just the square root, it's the inverse of these two. And so because I'm asking for helium to methane, you need to make sure to put helium on top, methane on the bottom. But because we're asking about this ratio of rates, you want to make sure that your rate of helium is on top, so the molar mass of helium needs to go on the bottom. Your rate of CH4 is on the bottom here, so you need to make sure that the molar mass of the CH4 goes on top in the next step. And last but not least, don't forget the square roots. After that, you would just plug in the values. Molar mass of C4 or CH4 is 16, molar mass of your helium is 4, and so all that this is really saying is that helium, because of the mass of how these things are set up and everything, helium is going to escape 2.002 times faster than your CH4 is going to escape. If you flop these things around, then it should make sense that CH4 is going to, again, travel half of the rate of He, because in this case, again, square root of 16 divided by 4, flop it around, you would have the square root of 1 over 2 in the long run here. Sorry, square root of 4 over 16, but this would have come out as 1 over 2. Alright, last thing. All these videos in this entire chapter, I've been talking about ideal gas, ideal gas, ideal gas. But one thing I did mention is ideal gases are make-believe. But luckily for us, if we use the model set up by the Kinetic-Molecular Theory, and if we use these assumptions about pressures and about volumes and about temperatures, and again, if we understand that this ideal gas is going to show us a linear relationship, then things just work out nicely for us. But remember, real gases do have volume because they are matter. Matter, by definition, has mass and takes up space. Additionally, real gases do experience attractive and repulsive forces between the particles. And if you don't believe me, wait until in Gen Chem 2, that's all you start talking about for the first few months is attractive and repulsive forces. And so this last bullet point is what you need to gather from this slide. And so I suggest you writing it down in a special color or highlight it, circle it, whatever. But real gases deviate most from ideal behavior at low temperatures and high pressures. What I mean by deviate most is real gases behave more real and less like ideal gases at low temperatures and high pressures. And so the ideal behavior at low temperature is an idea you can kind of, again, relate back to the fact at low temperatures, these gases move around much slower. And if you move around slower, you have more time to interact, you have more time to deviate away from this whole linear relationship. Same idea behind high pressure. At high pressures, you're forcing all these atoms closer and closer to one another. You're forcing them to interact. You're forcing them to become, again, a little bit more involved with each other than they ever wanted to be. But at high temperatures, these gases are moving around as fast as they can. They don't really have time to worry about the other atoms, and so they're perfectly okay, again, quote unquote, following these linear relationships. And so ideal gases behave the most like ideal gases at high temperatures and low pressures. Ideal gases behave the least ideal, or again, ideal gases behave more real at low temperatures and high pressures. And the last slide here, you don't have to, again, put too much investment in it. I just want to show you the fact that it gets so much worse than what you are trying to assume this is. And so van der Waals equation is something you may come across if you stick around in chemistry long enough. You may realize, again, this comes up like in physical chemistry, like quantum mechanics and thermodynamics. But in this situation, this PV equals nRT becomes a whole lot more complicated because this A and that B, those are variables that actually incorporate the relationship that, again, atoms do interact with one another. And that B, atoms do have volume. But for now, we don't want to deal with any of this stuff. We don't want to deal with partial derivatives that might come involved with all this. So you just need to be happy with PV equals nRT and realize it's not that bad. It could be so much worse. And so please last thing I have to say about this chapter is these problems may look kind of complicated. I'm not giving you the fact that they are like a simple piece of cake. But if you just take a deep breath, read through the questions without freaking out and panicking, the next thing you need to do is just identify your variables, pressure, volume, temperature, make sure they're in the correct units as atmosphere, liters, and Kelvin, and then from there, they're typically just plug and chug problems. Do a lot of practice problems with these, please.